Good day, I'm Marc Tabadero and I'm here to solve some of the problems regarding on concept in electronic communications. So for the first example is from a question from the EST Essentials by Engineer Fermar A. Fajardo. So the question is, calculate the thermal noise voltage of the two resistors, 5 kiloohms and 20 kiloohms for a 10 kilohertz bandwidth at 27 degrees Celsius if they connected in parallel. So we will have a given. So we have a given R sub 1 is equal to 5 kiloohms, then R sub 2 is equal to 20 kiloohms, and we have the bandwidth of 10 kilohertz and a temperature of 27 degrees Celsius. Since we need to find the thermal noise voltage, we will use the equation given. V sub n is equal to 4 kTBR. However, we need to find the total resistance. And since they are connected in parallel, we just need to find its product over sum. So we have the total resistance of 5 kiloohms times 20 kiloohms over 5 kiloohms plus 20 kiloohms is equal to 4 kiloohms. However, the temperature should be in terms of Kelvin. So we need to convert the given value of 27 degrees Celsius to Kelvin. Hence, we find the absolute temperature of 273 plus 27 is equal to 300 Kelvin. Now that we have found the total resistance and the absolute temperature, we can now find the thermal noise voltage. So just simply substitute all the given values with the Boltzmann constant of 1.38 times 10 raised to negative 23 joules per Kelvin. We get 8.1387958 times 10 raised to negative 7 volts. Or in engineering prefix, we have 813.8796 nanovolt or 0.8139 microvolts. So another question from Fajardo. So a three-stage has stages the following specifications. First stage with power gain and noise factor of 10 and 2 respectively, 25 and 4 for the second stage, and 30 and 5 for the third stage. Find the total noise factor. So we have the given solution. So we have the stage 1, which has a power gain of 10 and a noise factor of 2. Stage 2 has a power gain of 25 and a noise factor of 4. Stage 3 has a power gain of 30 and a noise factor of 5. So we will use the Fish formula in order to find the total noise factor. So we have this equation, F sub t is equal to F sub 1 plus F sub 2 minus 1 over G sub 1 plus F sub 3 minus 1 over G sub 1 times G sub 2. We will substitute all the given values on it and we get 2 plus 4 minus 1 over 10 plus 5 minus 1 over 10 times 25 and we get 2.316. So therefore, the total noise factor of the three-stage amplifier is 2.316. So for the third example is coming from Fajardo again. So the diode noise generator is required to produce 10 microvolts of noise in a receiver with an input impedance of 75 ohms resistive and a noise power bandwidth of 200 kilohertz. What is the total noise current and what must the current through the diode be? So first, we have two answers for this. In this problem, we need to determine first the noise current and the current through the diode B, which is the DC bias current of the given problem. So we have the given of V sub n is equal to 10 microvolts. We have the input impedance of 75 ohms. We have the given noise power bandwidth of 200 kilohertz. And we need to find the two unknown values. We all know that in Ohm's law that the current is the ratio of voltage to the impedance or just simply resistance in DC analysis. So we can express as I sub n is equal to V sub n over R or V sub n over Z, which is the input impedance. And also, we need, in order to determine the current to the diode, we need to use this equation. I sub n is equal to square root of 2b times I sub dc times q in order to find the current through the diode. So we need to find first the noise current. So just simply substitute the values and we get 133.3333 nanoampere. Then we need to find the I sub DC or the current through the diode. So by algebraic manipulation, we can express I sub DC in terms of I sub n to I sub n squared over 2BQ. Then substitute all the given values where Q is the electron charge, which is 1.06022 times 10 raised to negative 19 coulomb, and we get the current through the diode is 277.4004 milliampere. So another example is from Fajardo. A 350 kHz bandwidth produced by a tuned circuit will produce what effective noise bandwidth? So in this problem, we need to find the effective noise bandwidth. So we have the given equation of B sub EQ is equal to pi over 2 times B sub negative 3 dB, or also known as the half power bandwidth. Then since we have the given value of 350 kHz that was produced by a tuned circuit, therefore the given value of 350 kHz is the half power bandwidth. Then we will substitute it and we get 549.7787 kHz. Another question, not from Fajardo, but rather a question from a book by Wayne Tomasi. So the question is, for an amplifier with an output signal voltage of 4 volts, an output noise voltage of 0.005, and an input and resistance of 50 ohms, determine the signal to noise power ratio. So since we have the given output signal voltage and the output noise voltage, then we need just find the signal to noise power ratio in terms of decibel. So since we are using voltages as our ratio to the signal to noise power, then the multiplier in terms of decibel, which will be 20. So the solution to this is 20 times log of 4 volts over 0.005 volts, and we get in terms of decibel is 58.0618 decibel. So another example from Wayne Tomasi. Calculate the thermal noise power in watts and decibel in reference to 1 milliwatt for B is equal to 100 kilohertz and T is equal to 100 degrees Celsius. So we have this given solution. So we have the given B is equal to 100 kilohertz and T is the 100 degrees Celsius. Then we will use this equation to determine the thermal noise power. Since the given value of temperature is in Celsius, we need to convert into Kelvin. Hence, for the absolute temperature, the Kelvin would be 273 plus 100 is equal to 373 Kelvin. Now we found the thermal noise power of 0.5147 femtowatt. So that would be the thermal noise power in terms of watt. Note that the power in decibel in reference to 1 milliwatt is equal to 10 times log of P minus 1 milliwatt. So we substitute the given or the answered thermal noise power and we get in terms of dBm of negative 122.8841 dBm. So that would be the answer for this problem. Another problem, this time from a book entitled Electronic Communication System by George Kennedy. An amplifier operating over the frequency range of 455 to 460 kHz has a 200 kilo ohms input resistor. What is the RMS noise voltage at the input to this amplifier if the ambient temperature is 17 degrees Celsius? So we have the given, so we have a range of 455 to 460 kHz, which can be represented as f sub 1 is equal to 455 kHz and f sub 2 is equal to 460 kHz. we have the given resistor, which has a resistance value of 200 kilo ohms and an ambient temperature of 17 degrees Celsius. Since we need to find the RMS noise voltage, we need to use this equation. V RMS is equal to 4K TBR. Hence, we can also find the bandwidth of it by differentiating the f sub 2 and f sub 1, so that we can get B minus is equal to f sub 2 minus f sub 1. And also, we can convert the Celsius to Kelvin. For an absolute temperature, we get 273 plus 13, which is 300 Kelvin. So, for the bandwidth, its difference is 5 kilohertz and the absolute temperature is 300 Kelvin. Now we substitute and we get 4.0694 times 10 raised to negative 6 volts or 4.0694 microvolts. So, this problem is from Wayne Tomasi. Calculate the input signal to noise ratio for an amplifier with an output signal to noise ratio of 16 decibel and a noise figure of 5.4 decibel. So we have the given, so we have the noise figure 5.4 decibel and the output signal to noise ratio of 16 decibel. So we need to find the input signal to noise ratio. Note that the noise figure is 10 times log of the noise factor. Or noise factor is just simply the ratio of the input and output of the signal to noise ratio. Hence, we can find that f is equal to 10 raised to NF over 10. Then we substitute 10 raised to 5.4 over 10 and we get the noise factor of 3.4674. Then, in order to find the input signal to ratio, we just multiply it to the output signal to noise ratio and we get 55.4779 decibel. So, another problem is determine the bandwidth necessary to produce 800 femtowatt of thermal power at a temperature of 17 degrees Celsius. So, we have the given power, thermal power to be specific, we have 800 femtowatt and a temperature of 17 degrees Celsius. So we need to find the bandwidth and we have this given equation P sub n is equal to KT KB to determine the bandwidth, the unknown bandwidth rather. Then we all know that the Kelvin is equal to 273 plus the given Celsius of the temperature. Then we substitute it and we get 199.9 megahertz. So therefore, it needed 199.9 megahertz to produce 800 femtowatt of thermal power at a temperature of 17 degrees Celsius. And the last question is from Fajardo. So a 3-stage amplifier is to give a overall noise temperature no greater than 70 Kelvin. The overall gain of the amplifier is to be at least 45 decibel. The amplifier is to build by adding a low noise first stage existing amplifier with existing characteristics as follows. Stage 2 has 20 decibel power gain and 3 decibel noise figure. Stage 3 has 12 decibel power gain and 6 decibel noise figure. Calculate the maximum noise figure that the first stage can have. So we have two conditions given in this problem. So we have the overall noise temperature that should be no greater than 70 Kelvin and the overall gain of the amplifier is to be at least 45 decibel. So we have the given table in order to emphasize what this problem is all about. So we have two conditions, what I have said before. The overall temperature is no greater than 70 Kelvin. So we will use the equation of T sub EQ is equal to 290 times F minus 1 to determine the noise factor, particularly the total noise factor. So we manipulate the algebra and we get F is equal to 1 plus T sub EQ over 290, or just simply 1 plus 70 over 290, we get the total noise factor of 1.2414. Condition 2 states that the overall gain of the amplifier is to be at least 45 decibel. So since most of the power gain of the stages of the amplifier is decibel, we just simply add it up in order to find the overall gain of the amplifier. But since the unknown gain is in the first stage of the amplifier, so we need to find the gain of the first stage of the amplifier. So we have 45 decibel minus 20 decibel minus 15 decibel, and we get the gain of the first stage of the amplifier, which is 10 decibel. So we will create a graph again in order to convert the power gain and the noise figure from decibel to unitless. So for the stage 1, we have 10 decibel, which has a gain of 10 raised to 10 over 10. Stage 2 has 20 decibel or 10 raised to 20 over 10. Stage 3 has 15 decibel or 10 raised to 15 over 10. It also has, for the stage 2, the noise figure has 3 decibel, and it can, or just simply 10 over raised 3 over 10, unitless. And stage 3 has a noise figure of 10 raised to 6 over 10. So we will use the Friis formula to determine the noise factor of the first stage of the amplifier, since the total noise factor is now being computed, which is 1.2414. So we substitute and we get 1.1389. Then the question is, calculate the maximum noise figure that the first stage can have. So we just simply convert the noise factor into a noise figure by this equation. NF sub 1 is equal to 10 times log F sub 1. Then we substitute the computed noise factor of the first stage of the amplifier, and we get 0.5647 decibel. Therefore, the maximum noise figure that the first stage can have is 0.5647 decibel. And that concludes the concept of noise in electronic communication circuits.